Let's do an example. Let's try to compute the following triple integral. The triple integral over a region A of Z with respect to V. Well, the region E here is a solid. Give me 1 minute. It's okay. Just want to stop the chatting. So where E is the following side. A solid bounded by 4 planes in R3. So the first plane has equation x equals 0. So in R3, x equal to 0 is a plane. You will see later. The second plane is y equal to 0. And the third, you can guess, is z equal to 0. So we have 3 planes in R3, but that's not enough to bound a solid. I need 1 more. This time, I am going to look at x plus y plus z equal 1. Okay. All these are planes in R3. So let's draw the solid. So we have R3. The x, y, z space. Okay. Now when x is equal to 0, then this means that any point in R3 has the x coordinate equal to 0. We get the y-z plane. Right? When y is equal to 0, we get the x-z plane. And when z is equal to 0, we only get the xy plane. Okay? Now we are going to look at this first quadrant only. Okay? All right. Now, if we look at the first quadrant, I am going to look at x plus y plus z equal 1. Well, when z is equal to 0, we get a line. Joining these 2 points. Right? Now, when y is equal to 0, we are on the x-z plane, and we have the line given by x plus z equal 1.
Sir.
Yes.
So when z equals 0, so the point from x equals 1 to y equals 1, is that just a straight point? Is that just a straight line or a curved line?
A straight line, certainly.
Straight line?
Okay. When z is equal to 0, x plus y equal 1.
And y equals 1 minus x.
No. When z is equal to 0, x plus y is 1. And that's a straight line.
Okay.
Right? With slope equal to -1. Okay. And finally, we are going to look at the line on the y-z plane. So you can see that is a straight line, not passing through the origin, but passing through these 2 points. And the slope is also -1. So we have a solid bounded by the xy plane, the yz plane, and the xz plane, together with this triangular plane. That's the solid E. Okay. And the projection of the solid E on the xy plane is this triangle. And I can call that B. Okay. So that's the setup. Well, we cannot imagine what the function looks like, even for a simple function. When we integrate on a solid which is already in R3. So we simply do the calculations. So for triple integration, all you can see is the solid on which you are integrating. Okay. So solution. Now let's look at a triple integral again. Now, how did we define a triple integral on Monday? Well, we look at special regions on which we are integrating. And in this case, or the regions that we are looking at are actually regions whose projections on the xy plane is a good domain. Now, if you project this region, which is a tetrahedron, I mentioned that before. When you project this onto the xy plane, what do you get? D. But what is D? A triangle. So you can think of this triangle as the lower surface. And then you go up. To the triangle, assuming that you can see the line, assuming that this tetrahedron is made of glass. Okay. Then you go up to this point. So from this point, you go up to this point, and this upper point here is on the triangle. So you can think of this triangle as the upper surface. Correct? All right. So if you remember on Monday, we treated this integral as the double integral on the projection in the xy plane. And then you integrate from the lower surface. to the upper surface. Of the function set. Now, if you integrate from this lower surface to the upper surface, you are actually integrating with respect to z, the vertical line. So this is pz. And after you have done this, the z variable will disappear, leaving behind a function of xy only on D. So we integrate the resulting function with respect to A on D. So this is what we need to do. Well, as I said before, the lower surface is this triangle. So U1 at xy can be taken to be 0. And then you are going up to this upper surface. Now, what is this upper surface? We have x plus y plus z equal 1. So z is 1 minus x minus y. Correct? And then you have z with respect to z. And after that, you integrate with respect to A, the area on D. Okay? So this is the way to set up the integral up to the point mentioned on Monday. And then we don't need this anymore. We have reduced this triple integral to a double integral. But how do we evaluate a double integral on D? So now I am going to move things around and put the region B in the proper position. Okay. And we have a triangle like this. This is B. Now, we are going to integrate this function of x and y on the region D. So the inside integral remains as is the same thing. And now I have to integrate with respect to D of this function. So I fix a point X, and then I integrate with respect to Y from the point X to this point. And what is this point? What's Y equal to here?
1 minus x.
1 minus X. And then you move this line from the origin to 1. Okay, well, of course, this line here is of varying length. When it's here, the length of the line is 1. And then when you move, it also shrinks to a single point. So we are going to get the integral from 0 to 1, and then the integral, and this y actually goes from 0 to 1 minus x. And then we have dy dx. Okay, this is how to set up a triple integral. And that's the main thing about multiple integrals. You have to set it up. And then the rest is first year integration. Okay. But for simple triple integrals, I expect you to be able to compute to the final answer. Okay. All right. So let's see what we are going to get. So we have the integral from 0 to 1. And the integral from 0 to 1 minus x. when you integrate z, what do you get?
Z square over 2.
Z squared over 2, right? This is what everybody should know. And then we evaluate at 0 and 1 minus x minus y. So you see, this is basic calculus in first year. I mean the integration, not the setting up of the integrals. And then I have dy dx. Right? Well, we evaluate z at 1 minus x minus y. And then z at 0, and we subtract. So we get the integral from 0 to 1. Following the integral from 0 to 1 minus x. And this is how the 1/2 can be taken out. And then I have 1 minus x minus y squared. And then dy. And dx. This is what I said earlier. When you integrate with respect to z to get z squared over 2. And then after evaluation at the limits. Okay, maybe it's not good to call them limits. When you evaluate them at the endpoints and subtract, the z disappears. So no more z. Right? But I am used to call these limits. Maybe I should change and call them endpoints. All right. Now I am going to integrate this function with respect to y first and then x. So when you integrate with respect to y first, you have to keep x fixed. Okay? You have to treat it as a constant.
Yeah.
So by inspection, what do you get?
Would you get so negative bracket 1 minus x minus y to the power of 3 over 3?
Yeah.
Yeah. Okay.
The thing when you integrate has to be raised to the power 3.
And sir, you also have to have the negative in front because the negative y, right?
Yeah.
Okay.
Let me write this. So we are going to have 1 minus x minus y to the power 3 over 3. And there should be a minus sign in front because there is a minus sign here. And then you evaluate at the endpoints. So this is done by inspection. But not every student can do it.
Excuse me, Prof.
Like this. Yes.
I think you left one of the integrals.
Oh. No.
Yeah, don't you have to take the integral 1 minus
Yeah.
x 0? Yeah.
You are right.
Yeah, just put a bracket around it.
And I have a bracket run. Now, not every student can integrate by inspection. Well, if you don't believe it, then you can differentiate this function. And you will see that you will get this back. When you differentiate with respect to y, 3 comes down, canceling this. So we have square. But then you have to differentiate it inside. This goes away because x is constant with respect to y, and you get this minus 1 out to cancel this, and that's why you get that. There are many steps. Okay. But I am used to integrate much more complicated functions, so I can do it easily. But in case you cannot do it easily, what do you do? If you want to integrate this,
Could you just like expand it and then just integrate it with respect to y and then?
that's also okay. But there's an easier way.
Use substitution.
You use a substitution. You put
Yeah.
u equal 1 minus x minus y. When you expand it, you have so many terms. Okay. So you use a substitution.
But sir, would that give you the negative sign in front though, if you do that? So say you have u squared and there's u to the power 3 over 3. How would it give you the negative sign?
That's a good thing. It comes from the endpoints, the limits.
Oh, okay.
Okay. First of all, you switch this. And then you switch back. Okay. Okay, let me show. So you put u equal 1 minus x. This is a common mistake for students. When y is equal to 0, u is 1 minus x, right? So you put 1 minus x here. And then when y is 1 minus x, u is 0. They interchange. We don't want that. So we have to flip them back to the proper position. Then you introduce a minus sign. Okay?
Also, so that's where the minus sign comes from because you flip it. Okay.
Okay,
All right, makes sense.
okay. So let me try to evaluate. I can pull this minus 1/3 out. So it's minus 1/6 times the integral from 0 to 1 of the following thing. You put y equal 1 minus x, you get 0. And then you put y equal to 0, you get 1 minus x. So I have 0 minus 1 minus x to the cube. So I should have this minus sign here because this minus sign would disappear already. So we have 1 minus x to the power 3. Isn't it? Yeah. Yeah.
Answer the 1/6 becomes positive because when y equals to 0.
So first of all, you put
Yeah,
1,
that equals 0.
you get 0. And then you subtract minus 1 minus x to the 3.
Oh, okay.
Minus already cancel out this negative sign.
Okay.
So we get this. So finally, we are done to this first year integral. So this is 1/6 times the integral from 0 to 1. And again, if you could do the previous integral by inspection, you should be able to do this by inspection also. So I am going to have minus 1 minus x to the 4 over 4. And then you evaluate at 0 and 1 and subtract. So as before, when you put x equal to 1, you get 0. When you put x equal to 0, you get minus 1/4. So I have 0 minus 1/4, which is 1/4. And you multiply it by 1/6. So it's 1/24. So you can see the whole pattern here. From a triple integral, you reduce to a double integral. From a double integral, you reduce to a single integral of one variable. It's layers by layer. So I remember a story. Well, I was chair of the department before, about 10 years ago. For almost 10 years, I talked to the dean. Well, chairs and deans are usually enemies. And we talked about hiring people. And then I told the dean, he did not like me too much. And then I talked, well, not the present dean, that dean left already. So it doesn't hurt without mentioning the name. And then I said, in mathematics, it's layer after layer. And then he immediately said, I don't like layers. I said, well, whether you like it or not, it's a fact. Okay, all right. This is basically what I want to talk about today. But since I have some time, for sure I won't go over time today. Let me give you a preview of coming attraction. I am going to look at triple integrals. Actually, mathematics is really layers by layers without the prerequisite. Sometimes it's hard for you to go very far. Or let me today just mention cylindrical coordinates, because I have not written this down in the notes. I will have to write this down in the notes for the next lecture. Let me just talk about cylindrical coordinates. Which will take just 2 minutes. But if you talk about triple integrals in cylindrical coordinates, it may take half an hour. So we have R3. I have a point in R3. Okay. So we let P. With coordinates X, Y, and Z. Be a point in R3. So every point can be specified by theory numbers. But these are not the only theory numbers. I can drop a perpendicular from the point XYZ to the XYZ space, the R3. This XYZ space is always a backdrop for what's happening. And then I am going to have X and Y, right? This is X and Y. Or XY0, but I'm not going to be pedantic enough to write down 0 as well. So this is the X coordinate. And this is the Y coordinate. Okay. Now, this point in the XY plane has polar coordinates. You join the origin to the point XY, and you are going to look at the angle from X to this radius. This is the angle theta, and this is the radius. So this point can be,
Sir,
yeah.
What's that variable that you used for the line from the origin to XY?
That's all, the length,
R? Okay.
okay? This the length, the radius. So it can be specified. And of course, this line here is set as this set. So it can be specified by R theta and Z. Where X is R cosine theta, Y is the R set theta, and Z remains the same. Okay? And we call this the cylindrical coordinates.
Sir, just a heads up, it's 121.
Okay. And you write down this thing. So R theta, so still over time. The cylindrical coordinates. Actually, I did not want to talk about this today. But it's all right. So cylindrical coordinates are not too difficult. You only use polar coordinates for the base point in the XY plane. And the Z coordinate remains intact. All right. With cylindrical coordinates, you are going to see more interesting examples. Well, interesting means more challenging. Questions?
I was gonna ask, do you know like the chapters for what's gonna be on the next test? As like last time you gave us like 14.1.2, so we could like start studying.
Well, I think I mentioned already. It will be everything from the first test to wherever we can get by the end of the week or next Monday.
Or so you're not gonna exclude any chapters like you did last test.
That's right.
Okay.
It's not accumulative.
Okay.
Okay. But the final exam is. Okay. This is why students usually do well during the test, but not so well for the final. You know why? Because in the test, you are examined on small chunks of material. And it's easier to digest, easier to absorb, and to present. And moreover, you have more time for the final, but the final exam period is quite stressful, especially in the old days, when you have to write the exam in a big gym anyway. Closed books and so on. So the pandemic helps a little bit for the students. Okay, I will tell you exactly what you are responsible for. Most likely up to cylindrical coordinates, excluding the sections that I haven't covered. But near the end of the lecture, if I have time, I may go back to a section in chapter 13. That's the maximum and minimum of functions of two variables with proofs.
Wait, is this in chapter 13 or 14?
The maximum and minimum,
Yeah.
chapter 13.
Oh, okay.
7. Okay, that's good for some of the students who may go into optimization, linear optimization, and so on. But depends on the time. Okay. But I think we have enough time.
How many more assignments do we have?
How many more assignments?
Yeah,
How many assignments do you have now?
we have on Friday, assignment 6 is due. So I think assignment 7 is on Friday.
Yeah, assignment 7 is on Friday, maybe 7 or 8.
Okay.
Well, at least 8, because after the test, you have 2 more weeks. And then for the last week, I will give you problems to do, but you don't have to hand it.
Okay.
Okay. So 8 assignments altogether. Okay.
All right, thanks, sir. Have a good day.
You too.